Clean it up, guys.
And I'll
And
be in
that
and
was
out.
my deepest, darkest secret right before we started recording. Glad I shared it with y'all. Ted, you must have like the panopticon, like you've got like, 10 different screens with like 10 different Zooms running at a given time. And
I think he's muted us.
yeah, but or he's paying attention to one of the other
Yeah.
dozen Zooms he has to keep up with.
That's the problem when you have more than one going. You got to kind of shut down the audio on one completely.
I wish that so I do a lot of breakout rooms because I like to put kids into small groups, and that seemed to be effective this year to kind of give them a space where they could interact a little bit better than just camera off silent in a 30-person Zoom. But what was obnoxious is that I couldn't like observe all the different breakout rooms at the same time because I kind of just want to listen in so I could jump in.
You also can't chat across breakout rooms, which annoyed
Yeah.
me. Like I'd really like to be able to, like the broadcast message, nobody reads it.
No, I wish that when you did breakout rooms, you could have an option to have a unified chat across all the breakout rooms.
Absolutely.
And for the host to have basically just have all the breakout rooms compiled into their same Zoom interface, so that then you could just switch where your audio and camera goes on the fly, but you always see, or you could choose to focus in on one group or not, because most of what I do is I have them work on virtual whiteboards, and so I just have all those pulled up on my screen so I could jump in and say, oh, you need some extra help, let me jump to your breakout room.
That's exactly what I did. I was using OneNote for it, so I just click through the groups, and then if they didn't really need me to come in and holler at them, I would just write something. But if something went really wrong, I would pop in there.
Yeah.
But I wonder how much more they're going to work on that type of functionality if we're not using it for these purposes anymore.
I don't keep up with stocks, but I have to imagine Zoom's already hit its peak after, now that things are starting to reopen and return to normal. I would not mind teaching, one class a semester via Zoom, or one thing I do hope we definitely keep is like I would not mind teaching my class over Zoom if I'm like traveling to a conference, right? It's actually probably easier for me to just step away for 50 minutes during a conference to just do a Zoom with my students than get somebody else prepared to go in and cover for me.
So true.
Or if I'm like, sick, I'm well enough, I can sit up at my computer in my guest room, but I don't want to go into the office. Then I'll probably just have a Zoom, as a backup for the foreseeable future.
Office hours as well. I've really enjoyed Zoom office hours.
Yeah, absolutely. I'll definitely keep that as well. I may little short office hours right before and after class, and then the big office hours I'll just do through Zoom, or have the option I'll be on Zoom, or you can come by my office if I'm actually there.
One of the other nice things is all the seminars that have gone virtual. That's been really nice. Catch stuff from all over the world.
Yeah, I've definitely taken advantage of that. Although there's almost too many options. In fact, it's always disappointing because I have like two the Carolinas topology seminars at the same time as a open educational resources seminar run by AIM, and so I have to pick every week which one I'm going to go to, and it's
I'll say the virtual donuts at the North Carolina seminar aren't as good as the regular ones. That's the only problem. About
Where this is
9:29.
probably headed, though, is that universities won't pay travel.
Yeah. So it's about 9:30 right now. Should we wait another minute to see if people are still rolling in, or you want to get started?
Wait a minute. 8:30 conference time.
Yeah. So I just saw a couple more people pop in, so I thought I might wait just a little bit.
I'm one of the lucky folks that lives in the same time zone as the conference, so I don't have to do any arithmetic in my head to keep on
Surprising how
schedule.
difficult subtracting 1 is, but I've been having trouble with it.
Subtracting 1's not difficult. It's remembering whether you're supposed to add or subtract for
Yeah.
me.
All right, so shall we go ahead and get started, Stephen?
Well, let's do it.
All right, well, it's my pleasure to introduce Stephen Klontz from the University of South Alabama. His talk is sure to be really fun because it's about games. He's going to speak to us about limited information strategies for infinite length games. And also he's put the slides in chat if you want to click and follow along that way.
Yeah, thanks for that introduction, Lynn, and thanks everybody. And I'll go ahead and maybe if I don't remember to, in about a few more minutes, we can repost that link. That's one other thing about Zoom that we were talking about, complaining about Zoom, is that the chat does not persist if you come in late. So we'll have to get those slide links back in there for folks to come in a minute or two. But yeah, and so thanks for the to the organizers. Thanks for the invitation to come and talk to y'all. I was super excited a year ago thinking I was going to get to do this at Murray. But I'm glad we finally got around to making this happen one way or another. So here's the abstract. You've read that, it's on the thing. Here's probably a better outline here. So I've got 4 basic topics I wanted to talk about with y'all today. The one I'm going to probably spend a good chunk of time on is actually just this pretty it's a good introduction. There's this game called Baker's Game, named after Matthew Baker at Georgia Tech, on the real numbers, and I think it's a really great illustration of the kind of work that those of us who play around with topological games. There's no topology necessary to play this game. This is a game that's played just with the real numbers, and I find it's my go-to when I talk to undergrads in particular about the kind of work that I do. And so for a general audience, I thought this would be a kind of a cool way to illustrate the flavor of this sort of work. And I'll kind of get into a bit more of a formal definition of these various limited information strategies that I like to study. The motivating example is definitely the Banach-Moser game, which y'all you may have seen a great talk yesterday by Arichi about a variation of that, which I thought was really cool. And so definitely check out that recording if you didn't get a chance to see that. And then I'm going to talk about most of what my work has been with selection games, particular types of games. And so I'll go through and talk about various ways that you can change strategies into other strategies in as much generality as possible. And then finally, I'll close out with the proximal game, which I haven't worked with in a few years, but it was how I got into all this. So I wanted to definitely end that with an interesting, I think, open question. So here's Baker's Game. Here's a wall of text. I think I'd rather just draw a picture for y'all though. So Baker's Game is a game played on the real numbers. And so we're going to have 2 players. So we'll have player 1, which picks left endpoints, and then player 2 picks right endpoints. And the way this game is played is that player 1 will pick a left endpoint. Player 2 will pick a right endpoint. Player 1 will then pick another left endpoint that is strictly between those 2. Player 2 will pick a right endpoint strictly between, and this will go on forever. All right, and what we're interested in is right here, I'll call it L, which is the limit as n goes to infinity of the ANs. And so that's how the game is played. Now, what's the point? Well, first of all, the notation I'm going to use for this game is G of W. So that's going to be what I like to call Baker's Game. And I call it Baker's Game just because he's put out a pretty nice article. I'll give you a link to it at the in my references at the end in Mathematics Magazine. So it really was intended for a general audience of mathematicians, which is why I like it. And so he has some results on this. I think he had a student. I think I found a thesis from a student who did a little bit of work on this as well. Okay, and then what's this W? Well, W is a subset of the real numbers, and that's what we would call the payoff set. And we call it the payoff set because one wins this game provided that L belongs to the payoff set. So, all right, so that's it. 2 wins otherwise. There are no ties. And of course, this is what we would call an infinite length game because this is not a game that you want to down and try and play. I don't know if Stu Baldwin's here, but I definitely remember that at Auburn when I was doing my dissertation, he had a great joke. I heard it many times. Had I ever finished any of these games I studied? And the answer is still no. But we can just, do what we always do and just take a look at what could happen if this was played and we have these sequences. And so we had to take the sequence and decide where's its limit and where does it land. So even though we can't play the game, why are we interested in this? Well, the game hopefully characterizes something specifically about this payoff set right here. Certain W's should be better for player 1. Certain W's should be better for player 2, in a sense. So let's go ahead and take a look at some of these results and see if we can convince ourselves of these facts. So first things first, if W is countable, then I claim that Bob has a winning strategy. Maybe I should illustrate that a little bit. So if W is countable, maybe it looks like, maybe I'll draw a new line for this. Okay. And if W is countable, maybe it looks like, I don't know. This is my terrible drawing of the rationals. That's my favorite countable set, right? Subset of the real line anyway. So what would 2 do that would guarantee that they're going to win this game for a countable set if W is countable? So W is a bunch of WNs for N in the naturals, which I use omega for that. Well, 2 has to wait till 1 plays their turn, and I claim it doesn't actually matter what the first play by 1 is. What would 2 want to do? Their goal is to not let the A's converge to a WN. So let's suppose that W0 was back over here. All right. Well, good news for 2. A is not going to converge to W0. It's off on the left. All right. But let's suppose W1 is over here on the right. All right. There's W1. Well, all right. Well, I can, as player 2, make sure that we're not going to converge there because I can pick it. I'm going to pick it and call that B0. All right. Again, I claim that we don't care too much where A1 is for this argument. So let's say it's right there. All right. And then, maybe W2 is here. Well, that's their own fault, not letting them converge to W2, even though there might be some more stuff over here. W3. And I guess I should mention that at any point in this argument, if there aren't any W's between A1 and B0, then 2's already won. It doesn't matter what happens the rest of the game, right? But we're going to assume that there's like the next one, W3 through W99 happen to be back over here for some reason, but here's W100. All right, well, I'm going to pick that. That's the next legal W to pick. That's basically all player 2 does, is it looks for the least indexed W whatever that's playable, and then they play it. And then what happens at the end of this game even if this countable set is dense, like the rationals say, can this L equal W 200? No, it can't, right? Because before round 200, I made sure to play it if it was legal, and it had to be legal if it's between all the A's and all the B's. So L can't be any of those W's, okay? And that's how player 2 has guaranteed victory in this particular game. All right, so if I've convinced you of this, and this is something that's not too hard to convince, undergraduates of, then maybe, I have to remind them this calculus 2, thing, monotonic bounded sequences converge. We teach that in calculus 2, it's the completeness property of the real line. Well, Alice is going to win if the payoff set is all real numbers, right? Because, well, the limit exists, right? Suprema exist. So this limit exists and it's a real number because, well, it could be. Well, that's a proof that the real numbers are uncountable right there. So this game provides us a way to check if a set is uncountable, or if a set is countable. Excuse me, if a set is uncountable. If Bob does not have a winning strategy, then we know that set is uncountable. Such as when Alice has a winning strategy, we know the set is uncountable. And so I like this particular proof just because, for one, I like games, and then two, it also avoids a little bit of the, I remember the first proof I saw was about using, decimal expansions and then tweaking a digit in the decimal expansion. But then you have to get into, but what if you produced 0.999 repeating, but you had 1.0 repeating in your list? This avoids all that sort of mess, and you get to play games, which is fun for me at least. Okay, this talk was about limited information. So how much information does Bob actually need to play this game? Okay, so if we think about this game, during each round, after the first, which is a little bit the initial round, which is a little different, but during future rounds, Bob has to pick a point that's between two previously chosen points. A's most recent point is AN plus 1. Bob's most recent point is BN. So I guess Bob has to know those two numbers at least, right? In order to be able to pick between them. Otherwise, Bob might pick an illegal number and they lose by default. The question though is, what about the whole rest of the game, right? At this stage right here at B2, Bob had to pick between A2 and B1. But what about all this other information? Now, to pick a legal move, that seems to not be important, right? Because they just have to be between A2 and B1. But what if, we're trying to prevent one from converging? This is only finitely much stuff, right? And also, since my own previous moves are not used, I don't know. Do we need to actually keep track of all that? I didn't down here, and the proof that if W is countable to strategy, all that 2 cares about are the most recent moves of each player, or I guess that would be B0 here. Because I took those 2 moves, I have this payoff set, which it's part of the game definition, so that's not part of the limited information here. I could ignore this. I didn't care. All I cared about was, what was Alice's most recent move? What was my most recent move? Let's inspect the real line, find the least indexed W that's between the 2 most recent moves, and that's going to be my move. But is that always true? If I have a strategy that used, for some reason, this perfect recollection of all the moves of both players, could I improve it to use less information? Well, one thing I want to point out, sometimes you read these proofs and they have, they define the strategy based on all the moves of both players, and that's never necessary, because if you're playing with a fixed strategy, if you want to know your own previous moves, and you know all the moves of your opponent, you can reconstruct your own previous moves if you need them, right? Each of these Bs came from the fixed strategy from the previous As. So notationally speaking, at least, I always like to write my perfect information strategies just in terms of my opponent's moves. And often that's all you really need anyway in practice. But if you need to reproduce your own moves, you could as a part of that, recursive definition of the strategy. But like I said, in general, you might need to know all the previous moves of your opponent depending on the game that you're playing, depending on what the win condition is, right? But since this is about convergence of a sequence, do I really need to know the first few moves of Alice, or do I just need to know what the two most recent moves are? And so this is something I was like, I thought about this a week ago. I was preparing this talk. I was like, I've never actually thought about this. It seems that I only need to know the two most recent moves, what we would call a coding strategy, for a reason that'll become apparent in a moment. But then I sat down and I wrote out a proof and I bugged Lynn about, because she's very good at these coding proofs. And so I thank you for you letting me shoot you a bunch of emails like, oh, how about this? Oh, this. And then I got a good, I think, proof out of that. Let me just give you the flavor of that. Okay. So I claim that if I have a perfect information strategy, I can always improve it to a coding strategy. Let us maybe draw a new real line. Okay. So what does this look like? So here's the picture of the proof that you write. The first thing that you'll need to have is in your back pocket, you'll need to have a function from the reals to finite sequences of real numbers. All right. And I tried to construct this with like Cantor sets, and then this is I really appreciate Lynn suggesting a more simple version. If you're curious, we can talk about that later at the end, where this comes from. I will just tell you right now, you take the equivalence classes of numbers that differ by a rational. Each equivalence class would be dense, and each equivalence class, there would be continuum many of these, right? So there exists an f from R to R, which is also size continuum, such that the inverse of every sequence, which is all the real numbers, I just don't like, this is just the inverse image, set image. So the f of x is equal to s is dense in R. Okay, so what's going to happen here? Well, player one's going to pick, we can't do anything about this. They pick their first move. So I'm trying to convince you that I can improve a perfect information strategy, which would determine, so let's say, let sigma be a winning perfect info. Strategy. So sigma takes that move and picks a real number. Okay, so I'm trying to construct a coding strategy, which I guess I'll do, I don't know, orange. We're going to define tau, which will be a winning, so unbeatable, for anything that A does or Alice does, to be a winning coding strategy. So it only uses the two most recent moves, the most recent move of each player, let's say that. So here's the problem if I just kept going, right? Alice picks an A1. Now, let's say that this is sigma of A0, A1. Okay. Tau, the first move, I could just, I might try naively just to make them exactly the same. All right. So that would be a coding strategy. Only one player has made a move, so I use that as the information. Actually, I'll get rid of that sequence there. Just call it A0. Okay. But I can't do this. So what do I know? I know, so call that B0 as well, just for convenience. I know A1 and B0, or let's do it B0 to A1, just to keep the order in which they were played. Okay, can I just make those equal to each other? And I have to be careful, and I go, well, no, unless I knew what A0 was, which this function has no idea what A0 is, I can't just do that. So I'm gonna have to be a little bit more clever about how I'm going about this. Okay, so here is what I'm gonna do. First, I'm gonna erase this failed attempt. Here's where the word code comes into play. So what I'm going to do, because I get to see my own previous moves, I'm going to encode all of Alice's previous moves into my own moves. So this is where this little function over here comes into play, is I'm going to take the sequence, I'm going to pick x0 greater than, or how about this? I'm going to pick x0 in the reals such that I need it to be a legal move. And I also want it to be better than what Sigma would have done. Okay. One thing that to know about this is that Bob is just about, all Bob's trying to do is reduce Alice's options, right? What Bob actually picks has nothing to do with who wins, other than reducing the options that Alice had to pick. So picking smaller numbers is always okay. It never hurts Bob to do that because it just reduces the amount of choices that Alice has to make. So I'm going to pick this x0 such that it's between A0 and also what Sigma would have done, that winning perfect info strategy. And I also want it to be such that using this density, I can always find something between two numbers where f of x0 is equal to that sequence. Okay. So let's suppose that ended up right here. In fact, I called it x0. That's actually the strategy. Let's call that tau of A0. So here's tau of A0. Okay. So one thing to note is that I wrote this A1 to be legal with respect to Sigma, but it's also, we could assume it's legal with respect to both tau and Sigma, because the eventual goal here is that if the A's are legal with tau was just a restriction of the options that Sigma provided. These A's are going to also be legal against Sigma. Okay, so these A's are going to, this play is going to be against this restricted tau now. All right, and we're going to keep on doing this. Eventually we're going to get to this AN plus 1. All right, what's going to happen? Well, Sigma would have done this, A0 through AN plus 1. Okay. And we know that if this is played against a tau, we make sure that these taus are always producing stuff less than what Sigma would have done. Then these A's are going to work against both Sigma and tau. All right, I'm going to make tau to be even more of a restriction. And here's the deal. All right, I'm going to take this tau. It's going to go right here. It's only going to rely on my own last move, which I'll call BN for short, and AN plus 1. And all I have to do is pick it such that it's less than the sigmas. How do I make sure it's less than the sigmas? Well, starting with this induction, I encoded all of the A's I couldn't see into my own previous move. So I can extract extract all the previous moves of the opponent from the BN. So I now know what I would have done against these A's with a sigma. All right. That way I can guarantee that my tau is a restriction of the choices that sigma would have provided to Alice. It's less than it, while still being legal, still greater than all the A's. Okay. All right. I need to make sure it's less than, like I did over here, while still being legal. But then also I need to make sure I, at that same step, do that same encoding process. So I can ensure that an plus 1 is less than tau of bn an plus 1 is less than what sigma would have done in the same game, seeing the same choices by Alice. And I can make sure that I pick this tau using density to encode that, not, I had all the previous A's, I get a new A that I get to encode, but because I encoded all finite sequences of reals densely into the real line, I can encode that new piece of information into the tau, which I'll get to read in the next stage of the game. And that's basically the proof right there. I always like these sorts of these games. It reminds me of the movie Memento. If you've seen that movie, it's a guy who has short-term memory or loss. He can't remember anything more than happened a few seconds ago. So he puts tattoos all over his own body in order to keep up with what the heck's going on in his life. And it's basically, he's employing this coding strategy where all he gets to know is the last tattoo he wrote on himself and what just happened in front of him. And he has to piece that together to figure out what the heck he's supposed to do next. It's a fun movie. I won't say more. I might risk spoiling it for you. So it's something to check out. Yeah, so a good question in chat. Can you make the encoding strategy without using the axiom of choice? I'm going to guess probably not, but I haven't thought about it. I am assuming the axiom of choice throughout this talk. So thanks for that clarification. I'd have to think about this a bit more in that situation. Okay. Yeah, I really like this game. So I spent a lot of my time talking about it. Let's go ahead and talk about, though, okay, limited information strategies and topology in general. What kind of research is being done on these things? So first things first, a few bits of notation. This up arrow notation is pretty common for perfect information strategies. Player A has a perfect information winning strategy for game G. And then I like to stick little words, code for up-winning coding strategy. So we have tactical strategies. So tactical strategies, also known as stationary strategies, those are strategies that don't use the most recent move of both players, but just the most recent move of the opponent. So that means that you're not able to do this kind of trickiness that I just showed you, where you could just encode all the previous moves of the game into your own previous move. Now, sometimes you can encode all the previous moves of the game into your opponent's move if you can somehow restrict what they pick. And or other times you could just abuse the structure of the game in some manner. Markov is like tactics, except that you also get the current round number. This is often necessary in games where your moves are restricted by the opponent, or rather, where your opponent can just pick the same thing over and over again for the entire game, like in a covering game. If your opponent picks the same open cover, you're picking finite sub-collections. If your opponent can pick the same cover every time, and you're just picking a finite sub-collection, the space is not compact, then you've lost. You have to have a round number to kind of seed you, to push, to make sure you're making progress throughout that game. And then finally, I like to talk about predetermined strategies. This uses the current round number and nothing else. I call it predetermined. You could call it zero Markov. There is this general notion of K tactics and K Markov strategies that use the most recent K moves of the opponent. So a 3 Markov would use the three most recent moves of the opponent and the round number. So predetermined is zero Markov. You just use the round number. I call these predetermined because you know what's going to happen before the game even begins. You don't care what your opponent does. You're just going to do this no matter what. Okay. And kind of the where all this kind of came from is really goes back to this Banach-Moser game. And so it comes from the Scottish book in 1935. Here's a picture of it from Wikipedia. You know, a bunch of mathematicians would meet up and take notes in the Scottish cafe. And one of the things that they puzzled over coffee and whatnot is this Banach-Moser game. And I like this game because it's probably the most pure, I guess. It's kind of essential. Like there's nothing going on other than you have a bunch of open sets. You have these nested open sets. So this rectangle is supposed to be a topological space. You have two players, empty, who's playing the green open sets, and non-empty is playing the blue ones. And they're nested within each other. All right. The goal, first player is trying to get an empty intersection. Second player is trying to get a non-empty intersection, and that's it. They just keep playing nested open sets, getting smaller and smaller. Second player is trying to make sure there's something that they're whittling down to, and player one's trying to make that not happen. So a few results to throw at you. If you are, if your space is a, copy of a co-meager subset of the reals, that characterizes non-empty having a winning strategy. All right. On the other hand, if it's meager on an open set, because empty is the first player, they get to pick this first open set. You don't have to worry about being meager across, the entire space, but there has to be an open set where you're meager. All right. Because then empty can pick that and pretend the whole thing was meager the whole time. Right. All right. Then that means empty has a winning strategy. And then using the axiom of choice, you can construct a set that's both non-meager and its complement is non-meager. It's called a Bernstein set. And in that case, what does that mean? Well, it's non-meager, so empty does not have a winning strategy, but its complement's also non-meager, so it's not co-meager. That means non-empty doesn't have a winning strategy. And this is a thing. This is an indeterminate game. Again, abusing the axiom of choice here. All right. You can create games. This is in violation of a theorem from game theory of finite games, where in these perfect information games, one player has a winning strategy, and if they don't, it's because if they did, their opponent could steal that strategy from them and create their own winning strategy. But there is no strategy stealing argument in infinite length games. You can have games where both players can't guarantee victory going into it. They just have to play it out and see who wins. And so the Banach-Moser game, I think why it gets a lot of attention is because of this more general property of topological spaces. Topological space has the bare property, if and only if empty cannot have a winning strategy. So it's not that non-empty has a winning strategy, but that empty cannot have a winning strategy, which in general is not equivalent. Okay. And then just like I illustrated with this real number game, you could write a proof that non-empty has a winning strategy if and only if non-empty has a winning coding strategy. So they don't have to, all they have to pay attention to are, to pick this blue circle right here, they don't have to pay attention to what empty played in the very first round. They can just pay attention to their most recent blue circle and the green one. Okay. And then non-empty has a winning Markov strategy if and only if non-empty has a winning tactical strategy. So basically, if you know the round number, that's a little redundant. You can basically encode that round number. You can pass that forward by picking smartly, because your opponent has to pick a subset of what you pick. And so that you could pass the information forward and then reuse that from with a tactic. All right. And then here's a really important result by Debs in 1985. There exists a completely regular space. Non-empty has a winning two tactical strategy. So they can win by knowing the two most recent moves of their opponent, but they can't win by knowing just the most recent move of the opponent. And there's this very famous conjecture by Telgarsky that says that this is going to continue, that if you have you take your favorite, natural number, mine's 100. All right. There's going to be a space X100 where, sure, non-empty can win the game with knowledge of 101 moves of the opponent, but they can't win if they only know 100 moves of the opponent. And so there's some evidence to go against this. The biggest piece of evidence, a proper proof, a very recent result from Brian Dal, Milovich, and Junglet, says that if you have a certain model of ZFC, GCH plus square, if you're familiar with that, all the squares actually, they strengthen it for the statement of this theorem. And then finally, if you have a regular space, although that's actually really quasi-regular, I believe, is the only assumption you really have to have here. In this scenario, you've got some structure in your topological space, you've got some structure in your model of set theory. Non-empty can take a winning perfect information strategy that uses all the moves of the opponent and reduce that to just needing to know the 2 most recent moves of the opponent. And so this is a couple things didn't surprise me about this. The fact that it was a pretty clever and technical, and it required some set theory to dig in there and prove this. That didn't surprise me. But there's a thing about this conjecture that makes it a very strong conjecture. Okay, this is not surprising. I'll show you some other games where knowing 2 moves is way more important than knowing 1 move. But knowing 3 moves is not as big of a leap from knowing 2 moves in general. And here's my intuition that I like to share with this. Okay, if you're playing a game and you have tactical or Markov information, so 1 tactic or 1 Markov, so you only know 1 move of your opponent, your strategy can use information given by the opponent. You've forgotten your own previous moves, okay? And without some sort of, it depends on the game. Sometimes you can encode your own previous moves or your opponent's previous moves into their moves by forcing them to do certain things. Some games you can't force them to do anything though. But if you know 2 or more moves, okay, even if you can't do this encoding trickery that I've been talking about, you can at least see a reaction from your opponent. And this is kind of a weird human, sort of way of looking at this, right? Because if I was playing a game in real life, you might have your opponent might have a tell, right? You would think about that as using that information to improve your own strategy. But even in this very passionate world of mathematics, it's not so much that the opponent will have a tell, like they're going to go, oh god, that was such a good move, I have to do this. It's that, oh, that was a good move, I have to do this. I have to do something to handle the fact that you made that move in the last round that you've now forgotten about, but I still had to deal with it. And you got to see from 1 move to the other how I pivot, even though you've forgotten all the previous moves of the game. If you have 2 or more moves in your pocket that you can remember, that you can see. And that turns out to be the technique that gets used a lot in these sorts of proofs that you have a 2 tactic or a 2 Markov strategy, but not a 1 Markov strategy. You can use that reaction to get enough information to win the game. All right, so Bach-Mazur games, where a lot of the attention I think is on these sorts of limited information strategies. I personally have gotten more into the selection games, and I realize I only have 10 minutes left, so let me just kind of make sure I can hit the high points here. So first of all, what is a selection game? So at its purest form, your first player has a collection A that has a bunch of other collections. Each round they pick a collection from A. Player 2 for the game G1 picks a single representative from each collection during each round, and they're trying to build something that belongs to B. Okay, so that's it. That's doesn't, there's no topology here necessarily, although that's where it gets used a lot of the time. G-fin is the same thing, only player 2 gets to pick finitely made things. Instead of just picking 1 representative, they can pick 2 or 7, right? And I should mention real quick the things I'm going to go through here. I'm working on a survey with Chris and Jared on trying to capture a lot of these different themes throughout the selection game, limited information or strategy conversion process. So let's talk about first player strategies. Okay. So there's two famous results by Horevich and Palakowski that say that, first of all, this SFIN, that's called the selection principle. If you haven't worked with these things before, you could just think of it. It's just, you don't have a winning predetermined. The first player does not have a winning predetermined strategy. They can't just, oh, excuse me, fix that. They can't just, before the game even starts, say, I'm going to pick this, then this, then this, then this, and then you do whatever you want each round. They have to actually pay attention to what the opponent picks each round and then make their next choice accordingly. But it turns out that for the Menger game, where the collections are all open covers of a space, so player one picks an open cover, player two picks a member of that open cover and tries to build up an open cover, then that turns out to be, it doesn't matter for the Menger game and the Rothberger game. You can pick them all ahead of time, or you can pick them paying very close attention to what's happening. It just doesn't matter for player one, either way. And if you want to learn about how this works, these are classic results, but there's a recent paper by Suzak and Saban that digs into the details here. And I was, they were doing it for just the open cover situation. I thought, okay, well, how much topology? This is kind of my theme is, all right, I see these proofs in various papers. That's the same proof. You just swapped out this topological object with this other topological object. How can we capture the essence of this proof? And mine was pretty weak. I won't even mention it, especially with the time. But I do want to point out, a couple months ago in the archive, I only saw it last week when I was preparing this talk. There's this fun lattice theory representation of these proofs. And I think this is going to show some promise. I don't know enough about it because I haven't read that paper yet, but I wanted to shout it out because this is exactly the kind of proof I like to see. If you could just take your thing and prove, rather than trying to do some game theory, you could prove that your selections are the V1s of a Palakowski lattice, then you get this for free. Okay. Likewise, really briefly, I want to mention that if you have some additional structure on AB, where they are what I like to call Gammalike, so it's like a gamma cover or a converging sequence, such that the members are all infinite and every infinite subset of a member is still a member. Every infinite subsequence of a converging sequence still converges to the same point. Then in that case, perfect information strategies are equivalent to predetermined strategies. And they're also equivalent to these Archangelski alpha principles, which is this generalization of the convergence principles of Archangelski alpha 1 through alpha 4. There's some limits to this. You're not going to have this magic proof that says that every selection principle is equivalent to not having a winning strategy in the game. It's true for omega covers, but it's not true for the omega X, which is sets that have a X as an accumulation point. There's a certain space where for a particular point, one does not have a predetermined strategy, that's the selection principle, but one does have a Markov strategy. And then also, even for open covers, there are games with compact covers and open covers where player one has a winning perfect information strategy, but no predetermined strategy. The selection principle is satisfied. All right. As for second player strategies, okay, this is definitely what I wanted to get into, is this idea of, in selection games, it's really obvious that knowing more than two moves is not important at all, because for player two, and the reason for this is because player one can't be restricted by whatever player two does. Player one can just pick the same thing over and over again. So what I was talking about earlier is that if player one picks the same thing over and over again, the only way you're going to move forward is if at least you know the round number, so you can keep changing up what you're doing. Now, what if you only know 200 moves of the opponent? What could you do to improve that so that you only had to know 2 moves? Well, you have to assume that your opponent is being kind of cute and just repeats the same move 199 times, right? If they do that and you only get to see 200 moves at a time, then you're only going to see 2 different choices at any given time of this game anyway. And we're talking about finite selection games. So it's great that you get to see that same choice 199 times, but you get to pick finitely many things to begin with. If you see the same information, whether you had 100 of the first and 100 of the second, or 3 of the first and 197 of the second, it doesn't matter. You have the same data in front of you. You could pick finitely often. And so this 2 Markov strategy just says, well, take this 200 Markov strategy and just union up everything I would have done if my opponent was just being cute and just repeating everything 199 times. And that would produce, in fact, literally the same choices, but you only use 2 moves of the opponent. All right. And on the other hand, 2 moves are greater than 1. The greatest, the easiest example of this is probably the 1-point Lindeloffification of the first uncountable cardinal. So have that be a discrete space of size omega 1. Throw in a non-isolated point whose neighborhoods are co-countable. Okay, that satisfies. Second player has a 2 Markov strategy, but not a 1 Markov strategy. That's a typo. That should be 2 does not have a 1 Markov strategy. The reason for that really quickly is that this is not a sigma compact space. If 2 has a Markov strategy in the Menger game, that has to be sigma compact for regular spaces. But 2 does have a 2 Markov strategy. Basically, it's that reaction thing I was talking about, right? You see how the opponent reacts. And either, what do you do the first round? You pick the neighborhood of infinity so that you only have to cover Calamity much stuff through the rest of the game. But if you forget what you picked, that neighborhood of infinity at the beginning of the game, then you have to have 2 moves of your opponent, because your opponent could ignore the fact that you're going to cover up that countable leftover, and then you're going to win by the end of the game. Or they're going to be tricky with the open covers that they pick to trick you into not knowing what that countable thing is. But because you see that reaction, you can take advantage of what are called almost compatible functions. This statement here is how I write that there are almost compatible functions from countable subsets of kappa to omega. This is finite to 1. These are injections. These are finite to 1. And that turns out to be enough for the Menger game. This is just another notation for the same thing as up here. And these turned out to be all related to these games of Skeepers, which are just about picking countable subsets of a cardinal and finite subsets of a cardinal, and trying to cover up the countable choices with the finite choices at the end of counting mini rounds. I am definitely almost out of time. Let me make sure I hit all the high points I wanted to hit. And these slides are going to be on my website, and we can put them back again in chat here one more time. But let's see here. When can perfect information be reduced to Markov? Well, there's these patterns, right? I showed that for second countable spaces in the Menger game, perfect info can be reduced to Markov. Barman and Dow showed that for countable spaces in the selectively separable game, perfect information can be reduced to Markov. It just has to do with the fact that if you have a second countable space, the only open covers we care about are basic open covers. You union up all the basic open covers, you get the basis, and that's countable. For dense subsets of a countable space, you union up all the dense sets, that's the countable space, and that's countable. You exploit the fact that the union of the selection set A is countable, and then you have to be okay with, if you pick more stuff than you needed, it should still work. That turns out to be all you need to improve a perfect information strategy for 2 in this selection game to a Markov winning strategy. All right. Equivalent games. A good thing about me running out of time is that we're going to have a lot of great talks later this morning. I get to moderate that session. I'm going to have a lot of fun hearing all these great talks about games. And so I think this is something that Chris and Jared will be talking about. So I think I'll just leave this to them about how to turn perfect strategies for a player in one game into a perfect strategy for another game. But in my view, these proofs up here I believe are due to Sakai. I did this stuff down here once upon a time, but it's really just Sakai's proof. It's just throwing in a few extra parentheses respectively into that proof. The logic kind of falls through, and so this is where Caravana and Holzhauser have done a lot of great work to try and capture for CP theory, or even more general function space theory. How do we take covers in one space and produce converging sets, or sets with an accumulation point at the zero function in the function space? As for duality, I talked about this, I think the last time we got to all meet in person. There's a really nice way to prove that, not just that. So one thing I think is important, I like to talk about predetermined strategies, is that rather than selection principles, is because a predetermined strategy for one has a dual for Markov strategies for two in many games, and vice versa. So predetermined strategies for one, only knowing the round number, in a selection game tends to be dual in other selection games for two, knowing Markov information. Two has to know the move of the opponent because they're picking from that choice. But otherwise, these things flip back and forth. And it turns out that there's a really simple thing to check. You go through proofs of duality, and they're like 2 or 3 pages long, but there's a common, really easy proof that you can do. All you have to do is convince yourself that for one game and the other game, first of all, the players switch. In this game, player 2 is trying to build something in B. In this game, they're trying to build something not in B. And then the relationship between A and R, what I call a reflection, is basically just a quick check. I don't have time to go through it, but there's 3 lines right here. You prove that 3-line thing, and you automatically get duality, not just for perfect information, but for Markov information and even tactical information. And this gets you, like, these beautiful, if you study selection games, you'll get used to seeing these diagrams of, this is just 2-dimensional, 3-dimensional diagrams are out there as well. But all these cross, equivalences, that's just the reflection duality argument. You just check that these neighborhoods here are reflections of these open covers here. It's a one-liner basically, and you get this kind of rich duality for free. Last thing I want to make sure I mention, this is how I got into these games. My first paper with Gary Grunhage was studying the proximal game by Jocelyn Bell. And I guess I'll just kind of get into this. The open question that I thought about years ago, I kind of set it to the side. Maybe I should think about it again. But it turns out if you take coarse and compact, that's equivalent to having a winning strategy in Bell's proximal game, but it's also having a winning strategy in a game due to Gary Grunhage. All right, for strong Everlane Compact, you don't get that nicely. It turns out to be the same as tactic proximal, but that's not the same thing as tactic strategies in Grunhage's game. But there's still this kind of in-between thing. Tactics, a single move. This is perfect information over here. All the moves. What if you know just the most recent move and the round number? Now, it's true, that it's very easy because just of a characterization of coarse and compact, strong Everlane Compact, and Everlane Compact into certain function spaces. You get proximal, tactic proximal, and Markov proximal for free. We've managed to reverse 2 of these. This last one's still open. It's every space where the the first player has a Markov strategy, Markov winning strategy in the proximal game. Does that characterize Everlane compactness? One way you get for free because it's embedding in a sigma star space, but the other one's still open. And I think that's something to think about. But yeah, there's a bunch of references. I'm going to put those links back in chat. I'll make sure I send it to everyone, not just Lynn. But I guess it's time for questions. Thank you guys for hanging out.
All right, let's thank Stephen. However you want to, with noise or with a little symbol. That ended much better than the movie Memento did. Does anybody have any questions?
Spoilers.
Questions?
Well, I have a general question. Well, elementary or whatever. When you have, is there a distinction between knowing the order in which the opponent played the previous moves and just knowing the previous moves regardless of the order?
So I haven't thought about that. So a lot of the times, though, right? Let's say you just got the set of previous moves and not the sequence of previous moves. If it's like a selection game where you get to pick finitely many things, then given the set of previous moves, you can just permute that set the finitely many different ways you could permute it. And then for all those finitely many different options that may have happened, you could make those choices and then combine them all together. And as long as it doesn't hurt you to pick extra stuff, then you get away with it. So certainly in that situation, having the set instead of the sequence doesn't make a difference. That said, I'm sure there's a game we could come up with, at least a toy example. I haven't come across one in practice that's used in topology, but I'm sure we could construct a game, clever. I mean, there's probably here's a really silly infinite length game, right? I make a choice from the integers. You have to every round tell me all my previous choices. All right. Then if you just have the set of previous choices and not the sequence of previous choices, you're going to have to get lucky, I guess, in that case. It's sort of similar to how it's very easy to prove that there are games for each integer such that the player has an n+1 tactic, but not an n tactic. But my if you want a game where the second player has a 101 tactic, but not a 100 tactic, I could construct that game for you, but I've never come across it. I haven't seen that for a topological game. I mean, that's Tilgarsi's conjecture, right? It'd have to be independent of ZFC, or it'd have to be non-regular for this to pan out. But it turns out that tends to not crop up, at least very easily or naturally.
Well, thanks.
Will has a question. Oh, sorry. Will has a question and also offered an answer about choice in chat.
Yeah, I'm going to look back. I saw that going on. I was like, I can't look at this because I have to keep talking, but I'll have to take a peek at that.
My question is about the Baker's game that you talked about near the beginning of your talk. Do you know under what circumstances that game is determined?
So I'll be honest with you. I'd been holding off on. I suspected this coding strategy result for a long time, and I'd put off trying to work on it just because I thought this would be a really good thing to throw, for an undergraduate or student for undergraduate research, because it's a very easy to get into sort of game. So I put off trying to prove this for exactly that reason, but then I thought for this talk it would be a good example, so I thought about it and was able to prove it. So things about like indeterminacy, I've only very abstractly thought about it, but I've purposely held off on it because I thought it'd be a good project for a student. And I've got a student actually this fall who's going to work with me doing some game stuff, and so I'm kind of hopeful that maybe I can answer your question in a year. That said, I need to go back and look at it. There was a paper, like I said, Baker, I believe I think it was an undergraduate thesis, like an honors thesis or something, that they wrote about this game that has some results that I should look at, and there might be some indeterminacy stuff in there, but definitely offhand I can't tell you right now. I'm sure that and one thing to note about this game, right, is that it's very the flavor is very similar to the Banach-Moser game, right? You're in a way, in fact, it's a restriction of the Banach-Moser game where you have to pick intervals instead of open sets, and your endpoints have to line up in a certain way from the previous endpoints. And so that's another thing that I think is that could be dug into that I haven't, just because this game's kind of a toy, but also because I think it would be a good project to work on for undergraduate research someday, is trying to sync up, like wire up this game to the Banach-Moser game somehow.
That was my question. So when I was looking at it, I was asking myself, what's the difference, right? Well, the players don't get to choose both endpoints. And the original Banach-Moser game was formulated on the line and then moved to topological spaces. So is there some way to formulate this in terms of, what are they called? Not pre-bases.
Pi bases.
Pi bases?
No, not pi bases.
Oh.
Like a collection of open sets whose finite intersections form a base. What's that called?
Subbases.
Subbases. Yeah, thank you.
Jared got it in chat, actually.
Oh, thanks.
Yeah.
Do you know of a formulation for general topological spaces of Baker's game that
No, that's actually the project I want to work on with my student.
Oh,
is
okay.
is trying to, or at least for linearly order. Well, certainly you can
Linear.
very easily define this for linearly ordered topological spaces. I guess you might need some sort of completeness in order for that limit to exist, or maybe you don't care, right? Maybe if the limit doesn't exist, then Alice loses by default. But yeah, you could. This is all good stuff, and I'm going to throw it at my student next year, and we'll have some fun with that. So thank you. Sorry, I don't have answers for you right now.
Okay, so Stephen's slides are posted, and I'm sure he's happy to accept more questions over email. Let's take our speaker again.
I have a website that I put in chat, and I'll put the link to the slides on my website. That might be, if you need to find them later, you don't have to copy it down. I'm on the Google. Thanks, everybody. That was fun.
All right, yeah, and so the schedule, I guess we have a coffee break now. Is that right? It doesn't explicitly say coffee, but
Iced coffee.
So I guess KP's allowed to have tea.
Yep, I'm going to make some. You think this is a donut?
I don't know enough geometric topology to be able to say.
Well, it's a teacup. So it's not a donut. If it were a coffee cup.
Yeah.
well, that sounds like it's going to be a fun project, Stephen.
Yeah, I'm looking forward to it. We're starting out in the fall. We're going to read Conway's. I always forget if it's on games and numbers or on numbers and games, because I think the surreal numbers are kind of a fun construct, and then you can get into linearly ordered spaces from those. So that'll give us a chance to talk about both, the topological infinite length games and also finite games, which are encoded as surreal numbers. So I'm not sure exactly what directions we'll end up going, but it'll be fun whatever way it goes. So he was a great student in my abstract algebra course this past spring, which was tough. It was a tough course to teach over Zoom. Like I felt like I did okay the past year teaching Zoom like differential equations, but abstract, first time I ever taught that course, and it's on Zoom with all cameras off, and I have a much better concept of how to give students well scaffolded problems in a differential equations course versus an abstract course where, especially with I feel like there's a much wider range of people coming into that kind of course in terms of mathematical preparation. Some students will get bored if I spend a lot of time on here's how you compute the composition of two permutations, and other students really needed more of that from me. But I guess we're still recording, so I guess I shouldn't.
Oh. I don't know if Ted can hear us. He's the one that
Ted,
controls.
quit tracking us.
No.
So this Conway's base 13 function, I've seen that before, and I need to refresh myself on what that is, but I do remember hearing about that, and that seems like a nice.
It's a counterexample to the converse of the IVT, I believe. It's surjective on every interval.
Cool.
Yeah, I should know better to forget to say I'm going to assume the axiom of choice throughout this talk, and I apologize in advance because that's how I think. But it's good to know when these things don't need choice.
How's San Francisco, Hayden?
It's not San Francisco, actually. In my living room. I wish it was. Be a nicer view.
I'm actually not sitting outside of my math building on campus. I'm in my guest room.
I am in front of my table.
I had a person that I was collaborating with on a project, over Zoom, and for the longest time, I did not realize that her really nice, beautiful living room was just a virtual background. I think it was her dream house.
One of my
not her-
colleagues did that. Yeah,
Yeah.
she had this beautiful, like, porch and everything. I thought, wow, you've got a nice house. And sometimes the backgrounds don't have a blurry line. I'm not sure how you fix that, but
I just gave a semi-plenary talk. What am I going to do now? I'm going to Disney World.
Okay, so Stephen, you're chairing, huh?
Oh, I better. Yeah, well, I don't need to rush over there. I've got 25 minutes, but I guess I do need to put some thought into who's talking, and
Okay.
I guess I've moderated a session before. Is there anything I need to do that's different than?
I don't think so. I mean,
Yeah.
I forgot to flag you down. You were keeping track of time without me, but I don't know. I feel like